Okay, let's dive deep into one of the biggest unsolved mysteries in all of mathematics.
Right. It's often called the holy grail of number theory for a reason.
It really is.
It's a problem that's, central to understanding numbers themselves, but its influence, well, it stretches surprisingly far into fields like physics, computation.
And even how we think about reality itself, which is pretty wild.
Absolutely.
And we're basing our deep dive today on material from Julio Chai's book, The Enigmas of the Riemann Hypothesis.
Yeah, Chai does a fantastic job, takes this really complex subject and makes the implications pretty accessible.
He really does. So our mission today for you listening is to unpack this material. We want to pull out the key insights so you can get a real handle on what the Riemann hypothesis actually is.
Why it's still got mathematicians hooked after all this time.
Exactly. And the whole fascinating quest to maybe finally solve it. Think of this as your kind of essential guide. I'm genuinely excited about some of the connections here. They're pretty mind-bending.
And I'm here to help navigate that landscape, connect some of those maybe unexpected dots, and, give it some context.
Great. Let's get started then.
Okay,
so let's unpack this. To really get the hypothesis, we kind of have to start with the basics, right? The fundamental building blocks. Prime numbers.
Right, primes. Numbers bigger than 1, only divisible by themselves, and 1. Like 2, 3, 5, 7, 11.
The atoms of arithmetic, basically.
Exactly. Chai's book uses a great analogy. The cornerstones of an infinite cathedral. They build everything else.
And people have been fascinated by them for forever. We're talking ancient Greeks like Pythagoras, right? They saw something almost mystical in numbers.
Definitely. And Euclid, his proof that there are infinitely many primes. Just elegant. A classic piece of math.
Then you've got the giants like Carl Friedrich Gauss, the prince of mathematics. He had this amazing intuition about how often primes pop up.
Yeah, he noticed they get rarer as numbers get bigger, but in a predictable way. Related to the logarithmic function. Yeah. That idea became the prime number theorem.
Which is incredible for his time.
Astonishingly accurate intuition. But even with that theorem, if you just look at a list of primes, they still seem, random.
Right, scattered at random, as Chai puts it, like stars that dot the night sky, no obvious connection.
Or maybe flowers in an infinite field. The pattern seems to fade the closer you look.
But mathematicians, they suspect there's something deeper, right? A hidden rhythm, an underlying order underneath all that apparent chaos.
Yeah, finding that order is like exploring an enchanted forest. Every little discovery feels like finding a hidden path. It's been a long search.
And it's not just, abstract mathematical curiosity driving this. Primes are actually critical for us today.
Oh, absolutely. They're the foundation upon which modern cryptographic systems are built. Really fundamental.
So every time you buy something online securely or send an encrypted message.
Yep. That security relies on how incredibly hard it is to take a really large number and figure out its prime factors. Their sort of unbreakable nature makes them guardians of secrecy.
A technological pillar of our digital age. That's a great way to put it.
So, you see, understanding if there's a deep order to these primes, well, it has huge implications, way beyond just pure math.
Which brings us naturally to the main tool Riemann used to hunt for this order, the zeta function.
Ah, the zeta function.
Yeah.
It's a really remarkable mathematical creation. Chai calls it a piece of conceptual engineering.
Because it reveals hidden connections.
Exactly, especially connections among numbers, and particularly involving the primes. It sort of encapsulates their essence.
Now, this wasn't totally out of the blue. It built on earlier work, right, by Leonhard Euler.
Oh, absolutely. Euler was already seeing primes not just as individual numbers, but as part of a bigger, more complex structure.
He found that amazing formula.
The Euler product formula, yeah. He connected an infinite sum, 1 plus 1 over 2 to the s, plus 1 over 3 to the s, and so on.
To an infinite product that involved only prime numbers.
It was groundbreaking. The first time primes were tied so clearly into one single, powerful function. He was mapping the constellation of stars, so to speak.
Okay, so Euler laid the groundwork. Then Bernhard Riemann steps in, 1859.
And his approach was, as Chai says, radically new. Just completely changed the game.
How so?
Well, instead of just looking at the zeta function for, regular whole numbers or even fractions, Riemann extended its domain. He started studying it on the complex plane.
Okay. The complex plane, let's just quickly clarify that. We're not just talking about the number line anymore.
Right. Think of the number line negatives, 0, positives as one dimension. The complex plane adds a second dimension, the imaginary dimension. So numbers now have two parts, a real part and an imaginary part.
It gives you more space to work mathematically.
Exactly. A richer space to analyze functions. And Riemann's genius was realizing that the zeta function's secrets about primes were revealed when you looked at it through this complex lens.
And the key to those secrets were the function's zeros.
Precisely. The zeros are the specific points, the specific complex numbers are where the zeta function's value becomes zero. Zero becomes zero. Riemann saw that the location of these zeros was deeply connected to how prime numbers are distributed.
Okay, here's where it gets really interesting then. This connection, this is the heart of the Riemann hypothesis itself.
It is. The hypothesis makes a very specific, very bold claim about where most of these zeros are located.
Which one?
Well, it states that all the non-trivial zeros of the zeta function lie on one single straight line in this complex plane.
A specific line.
Yeah, known as the critical line.
Okay, you said non-trivial zeros. Does that mean there are trivial?
There are some zeros that are actually quite